About the Askaryan effect, a proposal known as the Askaryan effect, stating that ultra-high energy neutrinos could be observed through their interaction in a dielectric medium, comes to the rescue. Fuji. Come, Fuji. So this problem with needing a very large detection volume is something that we have to address in radio Cherenkov or ultra high energy regime. And that's what we're going to talk about right now. So what is the Askaryan effect? Basically, the principle is that a relativistic ultra high energy neutrino would interact with a nucleus in a dielectric to produce a particle shower, traveling in the medium at a speed greater than the speed of light in the medium. So that particle shower that's created in the ice, in the case of, say, Cherenkov happening in the ice, or sorry, this interaction happening in the ice, that particle shower will then travel in the medium at a speed greater than the speed of light in the medium. Not the speed of light in vacuum, because that's a constant and you cannot go above that speed, but the speed of light in the medium of ice, maybe you could go at a higher speed than that. The particle shower would mainly consist of photons, electrons, and positrons. Very simple. So basically, when an ultra high energy relativistic neutrino, because remember, a neutrino is a very low mass, small, tiny little particle that does not interact with very many things, but we're talking about a very high energy, ultra high energy neutrino, which is going to be there's this big noise outside with the traffic. Okay, so we're talking about a relativistic ultra high energy neutrino because, so it's going to be going at a very high speed because it's a very low mass particle. So if it's ultra high energy, it basically means that it's going at a relativistic speed. Okay, so the principle is that a relativistic ultra high energy neutrino would interact. So at that point, basically, even though neutrinos for the most part don't interact with most things, but such a high energy neutrino is predicted to interact with other things, but the cross section is still low. It's not like it's going to happen all the time, but we do have some idea for, depending on the energy of the neutrino, what is its cross section for interaction with particles. And will, for example, there's papers on this. I think my advisor actually wrote one of them. So she is a particle physicist. Her name is Dr. Amy Connolly, and you can look her up. She has work on this herself, where basically we know that neutrinos are weakly interacting and they don't interact much generally. But as we get higher and higher energy neutrinos, theoretically, we expect them to interact, but with certain cross section. And we have seen that the cross section of this interaction is going to be higher if you have a higher energy neutrino, where you might even get a high energy neutrino to be stopped by the Earth. Because most of the time, neutrinos that are lower energy will just go through the Earth. What does that mean? Going through the Earth means that you did not interact the whole time with anything as you went through the Earth. Like all of the mass of the Earth is in your way and you just go through it like it's nothing. It's transparent to you, right? That just means that you're so introverted, probably so tiny, and probably just didn't give a frick about anything. You just go through the Earth like it's transparent to you. And that's what most neutrinos do. This is also the reason why some people thought, when they found dark matter, as in they found that there is this dark invisible matter that we cannot account for, we don't know what it is, but there's this extra matter in our own galaxy and in the universe that we don't understand. People thought that this dark matter could actually be neutrinos, because neutrinos kind of behave similarly in that sense. Turns out neutrinos are probably not dark matter, or they don't account for most of the dark matter in our own galaxy or elsewhere because they're too low mass. But this is the reason why. Neutrinos, for the most part, could probably just go